Hi there. Today we'll look at direct feedback alignment scales to modern deep learning tasks and architectures by Julia Launay, Jacopo Poli, François Boniface, and Florent Krzakala. So this paper, on a high level, it replaces the backpropagation algorithm in deep learning architectures with this algorithm called direct feedback alignment, which is more biologically plausible. The algorithm has been around for a while, but it hasn't yet been shown to be applicable to really modern big deep learning architectures and then perform on par with backprop on modern deep learning tasks. This paper, as I understand it, is the first one to demonstrate that it can do that. So this is very much an engineering paper, an applied paper, and we're going to mostly go into direct feedback alignment as such, and I don't think we're going to go too much into what the actual empirical findings are, because they, even though they're impressive and it's a good piece of engineering, I think they can be summarized pretty much by it works not yet on par with backpropagation, but into a promising direction. All right. As always, if you like content like this, consider sharing it out and leaving a like, and tell me in the comments what you like. Of course, subscribe if you aren't yet. That is, essential. Otherwise, how are you going to hear from me in the future? Okay, let's dive in. They say, despite being the workhorse of deep learning, the backpropagation algorithm is no panacea. It enforces sequential layer updates, thus preventing efficient parallelization of the training process. Furthermore, its biological plausibility is being challenged. Alternative schemes have been devised, yet under the constraints of synaptic asymmetry, none have scaled to modern deep learning tasks and architectures. Here we challenge this perspective and study the applicability of direct feedback alignment to neural view synthesis, recommender systems, geometric learning, and natural language processing. In contrast with previous studies limited to computer vision tasks, our findings show that it successfully trains a large range of state-of-the-art deep learning architectures with performance close to fine-tuned backpropagation. At variance with common beliefs, our work supports that challenging tasks can be tackled in the absence of weight transport. So there's a lot to unpack in this particular abstract right here. So first of all, what's the problem with backpropagation? Backpropagation, they have two quarrels right here. First of all, it's preventing efficient parallelization of the training process. So what does that mean? So in backpropagation, I'm pretty sure you all know basic backpropagation, but you have an input to a neural network, and the neural network has a bunch of layers. So the input will travel layer by layer, and at the end, you'll get some output. And your output, y hat, let's call it here what the neural network thinks, let's say it's a classifier, thinks that the class of this particular X should be. Now in the data set, you have your true label, and then you compare that to your output label, and you can compute a loss function. Now, the whole question of the backpropagation algorithm is, how do I need to change my layers of the neural network in order to make the loss as small as possible? And for that, you can use backpropagation. That means you can take that loss and you can backpropagate it down the layers in order to update each layer individually. So the first problem they have here with the backpropagation algorithm, and it's not, it's kind of a secondary problem, but it is sequential. So in order to update this layer right here, you need to have already backpropagated to this layer. And then you need to backpropagate further to this and to this layer. So it's a sequential task. You need to backpropagate down the layers again. Whereas what is more plausible, what would be more efficient if we could somehow update all the layers in parallel. But this is a minor quarrel. The bigger one is that backpropagation isn't biologically plausible. We know that in real neurons, you have your dendrites, your inputs, and you have your axon, and the signal only travels in one direction. We don't know of a feedback mechanism in true neurons in the brain that would allow for information sort of to flow in the opposite direction. There is information flowing in the opposite direction, but I think it's too slow, and it's so it's not really, it can't be, there's no analogous way of backpropagation. There's nothing in the brain that would take the role of the backpropagation algorithm. Specifically, if each layer is characterized by a weight matrix right here, what backpropagation does is it uses the transpose of that weight matrix to backpropagate. So these arrows to the front right here, they use the weight matrices, and these arrows to the back, they use the transposes of the weight matrices. So the transposes of the weight matrices sort of relay the information of what needs to change, that would be the loss, what needs to change to make the loss as small as possible. They relay this information down to the other layers. And we don't know of any biological analogy to this mechanism right here. This transpose, it acts as sort of a layer inverse, and that is called weight transport. So weight transport means that you can do something like the transpose of the weights, basically to bring information from the next layer back to this layer. And in biology, we don't have this. And in direct feedback alignment, we don't have this either. So direct feedback alignment, the next thing here in this abstract, is the algorithm that they are going to apply here. Direct feedback alignment, and we'll go into what it is, but it is more biologically plausible in that what it does is it takes the loss somehow and it distributes it globally to all of these layers like this. And it does so without requiring these transposes and also without requiring these sequential steps. So both of their proposed problems here would be solved by this. They say that in contrast with previous studies limited to computer vision tasks. So what people have tried to do is they have tried to apply this DFA algorithm to computer vision tasks. But in computer vision, most architectures are CNNs. And as I understand it, as far as I understand it, DFA can only right now be applied to linear layers. So something that is WX plus B and then a nonlinearity. It cannot, even though you can write the CNN as like a linear layer with constraints, as I read this paper, I think to interpret that you can only apply DFA to fully connected layers or things that look kind of like fully connected layers. So what they're going to do in their experiments is they're going to take these big architectures like transformers and replace parts of them with the parts that act as fully connected layers with DFA updates. So, well, they're not going to replace the layers, but they're going to replace the backpropagation part of it with DFA updates. It remains to say that they still use backpropagation at some places where they can't replace the updates with DFA, and that means where the layer isn't, a fully connected layer, or I guess is too big. They somehow have to make it work. So often they will not update, for example, the embedding layers and things like this. Okay, so what they're saying is they go away from computer vision tasks, because if you go to computer vision and the CNNs rule that world, right? You can only do feed-forward layers, fully connected layers. You're going to lose already. So yeah, it's kind of an unfair fight in that sense. But even in absence of that, they say we apply this to neural view synthesis, recommender systems, geometric learning, and natural language processing. So these are quite diverse tasks, and they're going to be quite diverse architectures that they're applying it to. For example, in geometric learning, I believe they do graph neural networks, and there they replace usually in graph neural networks, there are fully connected layers that connect the vertices and the edges together and compute properties of them. So that's a pretty good point for using DFA, right? Because what you're looking for is state-of-the-art tasks and architectures that still employ fully connected layers, because there your algorithm can shine. Okay, so that's it. And they're basically going to show that performance is close to fine-tuned backpropagation. All right, so what is DFA? What is this direct feedback alignment? And for that, I actually want to jump papers right here and go to this other paper that describes DFA in a bit, not more detail, but in a graphic fashion. So this paper right here, Direct Feedback Alignment Provides Learning in Deep Neural Networks by Arild Noclund, shows some theoretical properties about DFA. Now, I don't want to go into the theory right here or in the math, but I mainly like this paper for this particular graphic right here. So in the backpropagation algorithm, as you can see, you forward propagate using these weight matrices, and then you backpropagate using the transposes of the weight matrices. Now, one step after that is this thing right here. It's called feedback alignment. It's not the same thing as direct feedback alignment. In feedback alignment, you simply say, well, I won't backprop using these transposes because I can't, because that's not biologically plausible. What I'll do is I'll use other matrices. And these other matrices are going to be random matrices. And by random matrices, we really mean a matrix that is of, the correct shape, the same shape as this W transpose. But each entry is going to be sampled from a random Gaussian, right? Now, I don't mean like the distribution of Gaussians, but you fix this matrix once at the beginning of training by sampling from Gaussian, and then you leave it there. And that's going to be the matrix that you use for relaying the signal back through the layers. Now, you might protest and say, wait, that's not going to work, because specifically this thing right here, that you need to know the weights here to know what you need to change in the lower layers. You need to somehow have that information in there. How are you going to know what to change? And that's a valid question, and I will give my opinion of why this works, okay? In 2 seconds. First, this is feedback alignment. So simply use random matrices to backpropagate, so to say. And then you have direct feedback alignment. And direct feedback alignment goes a step further, because in feedback alignment, you still do this in a sequential manner. Direct feedback alignment simply takes whatever the top change should be, the change to the top layer. So how do I need to change the top layer? And it backpropagates that in this global fashion to all the layers directly using random matrices, okay? And then this IFA we're not going to look at today because that's not relevant for this other paper. But I hope you can sort of see the overview here. So let's go back. Scroll. Okay, so here is the mathematical formulation of all of this, and it pays to look at it to understand what's going on. So they characterize a neural network right here as having n layers. Each neural network is the following. Each layer takes whatever is the output of the last layer, multiplies it by a weight matrix, and that's going to be your A quantity. You put A through a nonlinearity to obtain the next layer's input. Okay, so the H is the output of this layer and the input of the next layer. At the very end, your last output is going to be your estimation of the labels. So your last nonlinearity is probably going to be something like a softmax or something like this. Okay. So how can we have this as a concept in our heads? If you have the neural network right here, what you want to do is you want to forward prop, always using your weight matrix W, and then your nonlinearity of that particular layer, and then the last in the last layer you get your Y hat, as we saw before. Now the question is, how can we adjust this W right here to make Y hat more into the direction of Y? And here it's useful to think of the last layer as a vector output. Like usually we think of the loss function, but in all of these algorithms, they always start with the derivative of the loss function with respect to the last layer output, so AY. And AY is here right before the nonlinearity. If you remember, this was f of AY, and this here, I guess, is the softmax. So if this is a classifier, the AY here, those are the logits, and that's the output of your last layer. So it instead of having y and y hat right, y hat right here, it pays to maybe think of the output as a vector and the desired output as another vector. And the desired output is of course going to be one hot vector in the case of a classification, but if you think of it like this, then you will recognize, okay, I need to change, if this is my estimated output and I want to achieve this output, I need to change it into this direction, right, to get more into the same direction as the output I want. The entire question now becomes, how do I tell the lower layers about this change right here? This is the change that I want to make in the lower layers. How do I get the lower layers such that they provide me with that signal, with the green signal instead of the red signal? So I need to propagate this blue difference. In the backpropagation algorithm, you can simply ask the system, right? So we've built entire frameworks on being able to backpropagate, TensorFlow, PyTorch, JAX, whatever. Because with backpropagation, we can simply ask the system this question. So here is, how should I change the weights of my layer to make the loss smaller? You can just ask that. You can say, what's the gradient of the loss with respect to my weights? And the negative sign here is because you want to make the loss smaller. Okay, and that is going to be a straightforward calculation. How does that calculation go? It's going to involve this right here is the last layer's output. This right here, as you can see over here, is going to be, this is going to be whatever comes back from the backpropagation. So in backpropagation, you always have to think of, if you want to update these weights, you need two quantities. You need whatever comes from the bottom or came from the bottom during the forward pass, and whatever comes from the top during the backward pass. And this quantity here is going to be the one that came from the top. And it's basically how you need to change the next layer in order to make the loss happier. And by using this right here, you pull it back to this layer. So how do I need to change this layer? And here you see that dreaded transpose of that weight matrix. This is what we can't do in biology, but this is what backpropagation does. So it pulls back how you need to change the next layer. It pulls it back to this layer. So this quantity right here is basically, how do I need to change the output of this particular layer in order to make the loss happier? And then you multiply it by the signal that comes from the bottom, and that will give you how you need to change your weights, okay? So the green part is, how does the output of the layer need to change? And the multiplied by the blue part, it's how do the weights need to change? And of course, the nonlinearity is in there as well. But let's just leave the nonlinearity away, because it's really not important for this particular thing. So this is what backprop does. What does DFA do? DFA here again asks, how should I change the weights of layer I? And DFA says, well, first you need to compute this thing right here. This is, you see, the derivative of the loss with respect to AY. Now AY is the output of the last layer. These are, in our case, for example, your logits, okay? Note that this is still a gradient. So it's not like we can't differentiate anymore. We simply can't do backpropagation from layer to layer. Okay, so this is the quantity. How do we need to change the last layer's output? And we're going to take that and simply feed it through this random matrix and then multiply, again, let's leave this away, multiply it by this thing right here. So if I get my colors correct like this, again, you have your neural network. You want to update these weights. The green is what comes from the top. Now, it doesn't come from the next layer, but the green actually comes from all the way at the end. Sorry, you can't see that. I still have to get used to that new frame of view. So the green comes all the way from the end, and the blue comes from down here. Okay, so this is weird, right? Especially because this is just modulated by a random matrix. So how can this possibly work? That's the question. And I had some thoughts, but I haven't read too much about it, so I might be completely wrong, or this might be completely known in the community. I have no idea. I'll just give my opinion right here. So first of all, you have to compare this to backprop. So what's actually changing is this green part right here, right? We agree that this is the thing that's changing. And what do we say does the green part mean? The green part basically tells you how should the output of this layer change, okay? By adjusting the weights in the direction of the thing on the right side of the equality sign, you're going to change the output of the layer into the direction of that green part. Now, in backpropagation, the green part basically tells you how should the output of this layer change in order to make the loss as happy as possible. Now, we don't have that anymore. Here, we simply change the output of the layer into the direction of a random transformation of the change we would like to have in the output. Now, okay, that's the first thing is we understand what's different, and we understand what the green quantity means. Green quantity means how should the output of our layer change. Okay, second thing. If you look at the last layer of a neural network, that logits layer, right? What does it actually do? Let's say that's a three-dimensional last layer, which means you have three classes, right? If your last layer is three-dimensional, you have three classes. Each axis represents one class because you encode the classes as one hot vectors. So this might be C, your class label equals 0. This might be C equals 1. This might be C equals 2. If you have something that you forward propagate through your neural network, and let's say it comes out to be like this, what would you classify that as? Now, you classify that as whatever class has the biggest inner product with that vector, which would be the C equals 0 class right here. And what is this quantity going to be? How should you update this output in order to make the loss happier? Now that depends on your true label, but let's say your true label is actually the 0 label. Now what you want to do is you want to update that thing into the direction here, right? Such that it is more aligned with the axis. So what happens if you pull that back through a random matrix? Now, the thing you have to know about random matrices like this is that they do approximately preserve distances and angles. So technically, if you pull this back, what you're going to induce is another coordinate system in that other space. Now, this can be a higher or a lower dimensional space. Frankly, I don't care. But what you're going to induce is a coordinate system, and what do you pull through that B matrix? So this is the BI matrix. You fix it, right? This is really important. You fix it at the beginning of training. It's always the same. It preserves distances and angles approximately. You pull back that quantity. which is the, okay, my colors are all screwed, which is the green arrow over here. You pull back this green arrow here. So what does it mean? So the output right here, the output vector, that came from the lower layers, right? That's, you forward propagated that through your network. So maybe in this layer, it actually pointed here. We don't know, but let's say it pointed here, right? If we pull back the green thing, it might point here, okay? Now, this is, since it's a random matrix, we don't know. We know that the angle is approximately preserved, okay? But, you know, and the lengths are approximately preserved relative to each other. But it doesn't really tell you too much. So why is this useful? And to see why it's useful, you need to consider other inputs. We don't just input this one vector. We input a whole bunch of data. Now let's consider two other vectors. So first, I want to consider this, this blue vector right here. Now, the blue vector is also going to have a label of 0. So what does the blue vector's update look like? The blue vector is going to be pulled into this direction. And I also want to consider this red vector right here. The red vector is of class 1. So what does the red vector's update going to look like? Like this, right? And if I consider now the red and the blue vector in this space, right? I'll just draw them at random, like so, okay? What I do know, actually, that's for consistency, let's draw the blue somewhere here and the red somewhere here. What I do know is that the angles and distances are preserved. So what is the green thing going to look like? The update for the blue vector is going to be something like this. And the update for the red vector is going to maybe be something like this, you know, away from those. So what is happening in that lower space? You'll notice that the two vectors that are supposed to be in the same class, this and this, they are going to be pulled together. Now, the direction they're pulled in, that's determined by this random matrix. But we know they're going to be pulled together because they are pulled together in this space, in the final space. Okay? And they're going to be pulled apart from the red vector. Okay? Because that red vector is going to be pulled towards a different class in the last space. And since the distances and angles are approximately preserved, it's going to be pulled away from these in this space. So what this induces, in my opinion, is some sort of, it induces this coordinate system where if you make the last layer axis aligned because you want to classify it, it kind of clusters things that belong in the same class in these previous weight spaces, right? And if you do this layer by layer, so if you do this in layer K, and then you make the job easier for any layer K plus 1 that's in between here, right? Because now the things in the same class are already together pretty okay. Now you map it through a weight and the nonlinearity. They might, you know, intertwine a bit again, but they're more together than they would be otherwise. So you make the job for the next layer easier, which means that the next layer can even better cluster things. And what you'll end up with in this last layer is basically a cluster, or next to last layer is basically a clustering where everything that's supposed to be in the same class is together and far apart from each other. And since the last layer is the classification layer, it's going to have a really easy job separating those classes and performing good classification. So that's what I think is happening in this algorithm. So even though the layers don't know how to change to help the last layer, by the fact that these random matrices induce a clustering together, you know, by backpropagating these updates here, it helps the last layer makes its job really easy. And, that's all a classifier needs. And I want to show, again, this is my opinion. This is not anything of value. It's just my hypothesis of why something like this could work. I want to show you in this paper that I've shown you before right here, they do actually do these experiments with DFA, and they show that you can see top row shows feature obtained with backpropagation, bottom row shows features obtained with DFA. I think these are input and features. I'm not sure where exactly they are in the network, but you can see that this clustering clearly emerges. So, oh yeah, here, from left to right, input images, first hidden layer, second hidden layer, third hidden layer. So you can see that the clustering from layer to layer in backprop and also in DFA is better and better. So the reason why backprop is good maybe is just that because it also really induces clusterings like this. I don't know, maybe backprop does something on top of that, because I mean backprop has all the properties of this and more, right? But still, this is congruent with my hypothesis of what's happening. So what do they do with it? They take this algorithm and they apply it to these architectures. Now, let's, for example, look at one of them, this neural view synthesis with neural radiance fields. So neural radiance fields is a type of model to do this task of where you get a bunch of views of an object in 3D, or a bunch of views around an object, and you're supposed to render a new view. And you can see that the DFA parameter, or the DFA updated neural radiance field model, is pretty close to the backpropagation updated one. You can see it's a bit more blurry, but it works, right? And I think this paper is really trying to show that, look, this works. It doesn't work, extremely well, but it works. And it works on a level that hasn't been seen before. So here, if you consider these results, higher is better. On the synthetic data set here, even, you see that if you have the same model with backprop, it performs better than with DFA, but the DFA for that model performs better than these other baseline models that have themselves been trained with backpropagation. So it's definitely in the direction of being competitive. And that's the same thing they show with all of these experiments. So they apply this to graph networks, they apply this to transformers, and as I said, it's not there yet. You see that so in the transformers, they have these settings where in macro, they just use it DFA for the individual blocks, and micro, they use it for each layer. And I already told you that you still, in the attention mechanism, you still have to use backprop within the attention mechanism, but it is much more of a plausible algorithm than the backpropagation through the entire network. And they show that if they appropriately tweak the hyperparameters, they do get into the direction of something that's performant, at least with this macro strategy. Now, this is nowhere close to what the backpropagation algorithm achieves, but it's sort of an indication that if the community could work as much on this as it has worked on backpropagation, then probably will make a lot of, like, we could push this to a place where it does perform on par with backprop or very close to it. So I do invite you to go and look at the experiments. They have a lot of details on how they did it, and exactly how you have to change the architectures to make DFA work and the hyperparameters and so on. So that's really cool, and they have some more outputs right here of the view synthesis and so on. Yeah, if you are interested in that thing, I don't want to disrespect it. It's just, I don't think there's much point in me going over it. The results are always sort of the same, that DFA, it's not there yet, but it's a good direction. Yeah, I hope this was informative. Let me know If you disagree about my assessment of DFA, I could be completely wrong, or or this could be like well known to people already. So yeah, see you next time.